Welcome to CEC lectures. Myself Dr. Priti Jagwani. I am from Department of Computer Science, Aribhat College, University of Delhi. So in this present series of artificial intelligence, let me help you recall that in my previous lectures, we started about CSPs, which are more formally known as constraint satisfaction problems, and one of the problem which we looked into was a map coloring problem. So today's agenda of this lecture is going to be, we are going to look into different variations of these CSP formalism, and then we will be looking into a couple of crypt arithmetic problems. Now first of all, let me help you recall that in the previous lecture we looked into a map coloring problem where and also the scheduling the time limits for a kind of an assembly pipelining thing, in which we took the example of a car assembly or something of that sort. Now if we say the simplest kind of these constraint satisfaction problem involves some of the variables, and these variables definitely have kind of discrete domains and as well as finite domains. So if the variables are having discrete and finite domains, these constraint satisfaction problems of those type are categorically, we can say that they are simplest kind of CSPs. In this kind of sequence, we also need to formalize, or we also need to look into the 8 queen problem that can also be viewed as a finite domain constraint satisfaction problem, where the variables which are the kind of 8 queens q1 to q8 corresponds to the queens in the column 1 to 8, and the domain of these domain of each of these variables specify a possible kind of positioning in the form of row numbers for queen in that particular column. So di could be which is the domain set could be 1 2 3 4, anything starting from 1 to 8, which is actually the possible row numbers, we can say. Also the constraint, if we want to kind of define here, is no two queens can be in the same row or the kind of same diagonal. In the sense, we call it as no two queens can be in the attacking position. So this was kind of a finite domain. If we talk about a discrete domain which can be infinite, so for example, let us say we have a set of integers or maybe a set of strings. If we are not going to put a deadline on the job scheduling problem, which we have seen in my earlier lecture, there would be an infinite number of start times for each variable, and with infinite domains we must use the implicit constraints like t1 plus d1 less than equals to t2, which is the kind of timing for the first task, plus the duration taken by the first task will be less than equals to the duration will be less than equals to the timing of the second task. That means the start timing plus the duration of the first task must be less than equals to T2. That means the second task cannot be started if the first is not finished, if they are kind of in a sequence. So rather than explicit tuple of values within the infinite domains, we can use implicit constraints of this type, which is T1 plus D1 less than equals to T2. Now also, if we call about the algorithms which are there for linear constraints on integer variables, we have some special solution algorithm which are existing for these kind of situation or these kind of constraints, we can say, such as the one kind of we can say in which each variables appears only in the linear form. Now also it can be shown that if no algorithm exists for solving a general non-linear constraints on integer variables, we can say the problem is undecidable. Constraint satisfaction problems with continuous domains are actually kind of you can say is very common in the real world, and the best known category of continuous domain CSPs is that of linear programming problems, which are LPP, and I am sure that you are familiar with the domain. In LPP, linear programming problems, constraints must be linear equalities or inequalities. Linear programming problems can be solved in time polynomial in the number of variables. Now, these constraint satisfaction problem are there which are having different constraints and different objective functions. So, different constraints and different objective functions can be kind of studied in quadratic programming, or we can say second order conic programming, and so on and so forth. Also, in addition to examine the type of variables that can appear within these constraint satisfaction problems, it is also kind of very important or useful to look at the types of the constraints. The simplest, when we say type of constraint, so the simplest constraint will be unary constraints, where which restricts the value of a single variable. That means unary constraints is one which is operating on a single variable. So, for example of this kind could be map coloring problem. Now, it could be the case that the region South Australia will not tolerate or will not be filled with kind of green color or any other specific color. So, we can simply express this constraint with a unary constraint which says SA not equals to a green, where SA represents South Australia territory region, if you recall the previous problem, and the domains are red, green and blue, that are actually the colors which are going to be filled in that kind of region inside the map coloring problem. So, if South Australia not equals to green, that means this is simply a unary constraint which says South Australia cannot be colored in using the green color. Also, we can say that initial specification of the domain of a variable can also be seen as a unary constraint. Now, coming to the binary constraint, the first type is unary constraint, another one is a binary constraint. So, unary constraints was onto one variable, binary constraints relates to actually two variables. For example, if we say South Australia cannot be equals to New South Wales, that is kind of a binary constraint, because here we are using two variables, which one of them which is SA, another one is NSW. And a binary constraint satisfaction problem is one with only unary and binary constraints, and it can be represented as a constraint graph. Now, a constraints involving an arbitrary number of variables, we call it as a global constraint, but we call the constraint as a binary constraint, which if it is having only unary or binary constraints. So, the constraints can be on the basis of number of variables, it can be binary or unary constraints, or it can be the global constraint. Now, binary constraints can be represented using a constraint graph also, and that kind of we have seen in the previous lecture. Now, coming to within this constraint satisfaction problem, one which is a famous kind of a dimension of these constraint satisfaction problems is about crypt arithmetic problems. When I say crypt arithmetic, this actually is a problem in artificial intelligence, and it is kind of a constraint satisfaction puzzle which is having letters. Letters arranged in an arithmetic equation, and these letters are to be replaced by the digits starting from 0 to 9. The representation should be unique, with the goal in mind that the digit mapping we need to find, such digit mapping we need to find that makes the equation true. Now, this kind of crypt arithmetic problem is going to kind of serve as a classical demonstration of search algorithms, or we can say constraint propagation, or even kind of backtracking in AI. So, let us first of all try to understand this crypt arithmetic problem. So, this crypt arithmetic problem, one of the I can say a classical example of a crypt arithmetic problem is shown on the screen, which says 2 plus 2 equals to 4. So, here you can say we have some letters and we have an equation in which we are in kind of adding TWO along with TWO, and the answer should be FOUR. So, here each letter is going to stand for a distinct or for a unique digit, and the aim in which we are going to solve this crypt arithmetic problem is actually to find a substitution of digits for letters such that the resulting sum is arithmetically correct with the added restriction that no leading zeros are allowed. So, each and every kind of letter here will be represented by a digit, by a distinct digit I can say. That means you cannot repeat the digit, leading zeros are also not allowed, and we need to assign some of we need to assign values to this kind of crypt arithmetic problems, or to kind of or to the letters in these kind of crypt arithmetic problems, such that those kind of numbers are going to satisfy this kind of equation. So, whatever we are going to kind of replace for 2, whatever we are going to replace for t, whatever we are going to replace for w and o as well, some of these as written here shall be equals to the representation of FOUR. Now, each letter in this kind of crypt arithmetic puzzle represents a different digit, as I have already told you. So, kind of that is the first constraint which we need to represent, and this kind of constraint, that every letter in the crypt arithmetic puzzle represents a different digit, will be kind of denoted by a global constraint. Now, here this crypt arithmetic problem is going to give us, or is going to present an example of global constraint. It is not a unary or a binary constraint, because number of constraints, number of variables under these constraints are more. So, what all are the variables? So, variables are f, t, u, w, r and o. That means every digit is going to be a variable in this crypt arithmetic problem, and what we need to do in order to represent this global constraint, or in order to represent this constraint that each letter in this puzzle represents a different digit, the constraint will be all diff, and what all we are talking about here are f, t, u, w, r and o. And also it is not just this particular constraint, there is also an addition constraints on the 4 columns of the puzzle. How are we going to write those addition constraints? So, addition constraint, let us see how are we going to write this. So, for example, we have O plus O is going to be R, then there can be a carry from this R to the next column on the left, which is W plus W. So, here we are going to write O plus O may generate equals to R only, or it can generate a carry also. So, in order to accommodate that carry, we are going to write O plus O is equals to R plus 10 multiplied by C1. So, if there is no carry, then obviously the carry 1, which is a carry from this column O to column W, is going to be 0. So, then we can simply say O plus O equals to R. So, in order to accommodate that carry, whether it is 0 or 1, it is how are we going to write this? It is O plus O equals to R plus 10 dot C1. Also remember that leading zeros are not allowed. Each and every letter can be represented only using a single digit. So, what can be the maximum value of carry? So, the biggest digit which we can assign to a particular kind of digit is 9. So, 9 plus 9 maximum is going to be 18. In this case also the carry is going to be 1. So, the carry will always, in these kind of crypt arithmetic problems, the carry will be always either equals to 0 or equals to 1. Now, coming to the next column, now that next that column W plus W has got a carry which is represented by C1. So, now C1 plus W is going to be equals to U, plus it may generate kind of another query. So, another query will be kind of C2. So, again in order to accommodate the value of C2 either as 0 or 1, we are going to write it as U plus 10 dot C2. So, in the similar manner we have written 0 plus 0 is equals to R plus 10 dot C1. Here we are going to write C1, which is going to be included in this column W plus W, is equals to U plus 10 dot C2. Now, the two carries we have taken care of. Now, this is also a possibility that addition of this second column is going to generate another carry, which is C3. So, C3 we need to accommodate for the column T plus T. So, for example, so this C2 which was generated by W plus W, so C2 plus T is equals to O plus 10 dot C3. Now, please see, so from the first column onto the second column we have got a carry C1, from second column to third column we have got a carry C2. So, C2 plus T is equals to O plus T1 dot C3, and this C3 will be kind of actually carried over onto the fourth column, and in the fourth column we do not have anything from these kind of inputs, there is just a simple carry. So, C3 is equals to F. Now, first thing which is kind of equal, which is very kind of we can say very obvious from here is your C3 is equals to F, and that is equals to 1. Why I am saying so? Because leading zeros are not allowed. So, we cannot say F is equals to 0. So, F there has to be some carry, and the maximum carry which we can have in these kind of cryptarithmetic problems is nothing but 1. So, 1 is equals to F, and that is going to be our C3. So, that is the first thing which we are going to make sure from this kind of problem. Now, these kind of problems actually involve kind of putting a value satisfying the constraint, and if the constraints are not satisfied we can kind of backtrack and kind of look for another value. So, this is what actually is going to happen. So, backtracking is the main technique which is going to be used in order to solve these kind of cryptarithmetic problems. Here C1, C2, C3 what we were talking about were actually auxiliary variables. Why I am saying that auxiliary variable? Because these are the intermediate variables, temporary variables which are generated from the problem only, and these variables are representing the digits carried over into the tens column, into the hundreds columns, or into the thousand column, because unit columns we kind of in any case it is not going to generate any carry from the left column, because that itself is the leftmost column. Now, these constraints can also be represented in the form of a constraint hypergraph. Now, what all are the constraints? So, the first constraint was all diff, the value of all the digits should be different from each other, and the hypergraph which I am talking about that consists of ordinary nodes which are actually kind of we can say circles and the hypernodes. So, hypernodes are the square which represents the constraints. Now, that constraints can be kind of a binary constraints or more than that. So, if you need to kind of look into the constraints, the hypergraph of this 2 plus 2 equals to 4 cryptarithmetic problem, this will look like as the figure shown on the screen. So, the first square which you can see on the top is actually the constraint which says all different. That means the value of F, T, U, W, R, O is going to be kind of different from each other. Then you have the squares below this F, T, U, W, R, O. These are the variables. So, that is why they are kind of represented in the form of circles, and at the bottom of the this hypergraph you can also witness C1, C2 and C3 which are again in the circles, and these are exactly the kind of auxiliary variables. So, now you can see that C1 and C2 and C3 are actually represented in the form of kind of nodes, and they are connected with the these square boxes which represents constraints here using different links. So, for cryptarithmetic problem we can say that this is actually going to be a constraint representation of constraints, or one way of representation of constraints, which is actually what we call is the hypergraph, and all the constraints which we are which we were talking about can be represented here. So, all diff is the square box at the top, as well as the column addition constraints are represented by 4 square boxes in the middle auxiliary variables C1, C2, C3 represent the carry digits for the 3 columns from right to left in a way. The constraint which we have described so far have all been the absolute constraint, in which we can say that violation of the rules, violation of which rules out a potential solution. So, if we are going to violate these constraint, we are not going to find any kind of solution. So, violation of rules will result in the loss of a loss of potential solution. So, all these constraints are absolute constraints. Now, there are many real world constraint satisfaction problems that include preference constraints indicating which solutions are preferred. So, violation of these preference constraints can only we can say rule out a particular solution which is favoring or which is preferred, we can say, but we cannot say that it rules out the potential solution. It may rule out a particular preferred solution, but there are other which exist. So, for example, in a university class scheduling problem, if we say there are absolute constraints that no professor can teach 2 classes at the same time, or we can say in the same room at the same time there cannot be 2 classes, that is an absolute constraint. But we may also have some kind of preference constraints over here, where we can say Professor X might prefer teaching in the morning while Professor Y prefers teaching in the afternoon, and a schedule that has Professor X teaching at 2 p.m. would still be an allowable solution unless that professor happens to be maybe a department chair, but would not be the optimal one, we can say, because we have not kind of taken a we have not considered the preferences of that particular professor. But yes, still we are in a situation of an in an allowable solution, may not be optimal, that is kind of fine, we can say. This was about the crypt arithmetic problems. Another classical example of crypt arithmetic problems is being shown here on the screen, which is actually kind of send plus more equals to money. And if we want to kind of need to, so all different constraints is there. So, value of S, E, N, D, M, O, R, and then is going to be, and y also of course. So, it is going to be difference. So, the first constraint will be D plus E is going to result into y, maybe a carry onto the next column, which is N plus R will result into E, maybe a carry kind of into the next column. But certainly here also we have kind of 4 columns which are to be added, and the result is coming in kind of in 5 digits. So, the first digit M definitely that is going to be equals to kind of 1. So, the idea is to firstly kind of create a list of all the characters that need assigning values to get this problem solved, and use backtracking to assign all possible digits to the character. If all the characters are assigned, we can say return true, the puzzle is solved, or we can say kind of false otherwise. Or we can say if it is coming to false with a particular solution, consider the first unassigned character for every possible choice among the digits which are not used presently. If all the digits have been tried and nothing worked, return false in order to trigger the backtracking. And if you can see with so many carries and with so many different constraints, this send more money can be solved by keeping all the constraints in mind. The final results of this send more money will be something of this sort, Also, please remember that these kind of solutions of crypt arithmetic problems are not the kind of exclusive solution, in the sense there can be multiple solutions for any kind of crypt arithmetic problem, which is 2 plus 2 equals to 4 or send more money. This is one of the solutions which is going to satisfy or which is satisfying all the constraints, but definitely we cannot say that this is the only solution. So, crypt arithmetic problems, apart from this kind of crypt arithmetic, these kind of crypt arithmetic problems which we have just seen, these two examples, these couple of examples which we have seen are actually involving one particular kind of operation, which is the addition. Now, there can be crypt arithmetic problems which are going to be kind of in the form of, or which are going to utilize the operation of multiplication also. Another classical example of the crypt arithmetic problem is this one, which says base plus ball is equals to games, and on the right hand side the solution is given, and this solution is actually kind of we can say has been kind of determined with the help of this backtracking, assigning the characters, trying different unassigned characters, and then finally going to backtracking. If none of those assignment works, we will be kind of try other one. So, in this lecture what we have looked into is actually various dimensions of constraint satisfaction problems, and their kind of nitty-gritties, nuances we have looked into. Then one particular example of these crypt arithmetic problems which we have seen is actually the crypt arithmetic problems, and we have seen how to solve them couple of along with the couple of examples. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next with a different topic in the next lecture. Till then, take care. Goodbye.